welcome viewers to the last lecture of the lecture series on integral differential equation under the NPTEL courses. In all previous lectures, we have considered linear integral equations only. In this lecture, I am going to discuss about some solutions and properties of nonlinear integral equations. Of course, there are a wide variety of different types of nonlinear integral equations, and it is not possible to discuss all those type of equations in this single lecture, but I just want to give you some essence of these nonlinear integral equations because they produces two interesting properties of the solutions. Number one is the bifurcation of solution, and with help of this type of nonlinear integral equation we can explain the concept of singular solution. And another important property that we can explain, that some of the nonlinear integral equations, or you can say most of them, do not have unique solutions. With illustrative example, I will try to illustrate this phenomena, that how non-uniqueness of the solutions comes into the picture. So, we will be considering two types of nonlinear integral equations, that is nonlinear integral equations we may consider this yx equal to fx plus lambda integral a to b k x comma s g of ys ds. This is a nonlinear integral equation of Fredholm type. And nonlinear Volterra integral equation can be written as yx equal to fx plus lambda integral a to x k of x comma s g of ys ds. This is of Volterra type, where this g, capital G, is a function of y, which is a nonlinear function of y. And some example of these type of equations are yx is equal to 1 plus lambda integral 0 to 1 s of y square s ds. In this example, g is actually gy is actually y square. Similarly, another example is yx equal to x minus 5 by 6 plus integral 0 to 1 ys plus y square s ds. This is an Fredholm type integral equations, and one Volterra type nonlinear integral equation is yx equal to 1 minus x square minus x cube by 3 plus integral 0 to x y square s ds. These are some nonlinear Fredholm and Volterra type integral equations, and of course, these g may be some function like e to the power x, sin x, and some other combinations such that they are nonlinear functions. Once this gx is a nonlinear function of y, then equations of this type are actually known as nonlinear integral equations. So, first of all, we discuss the direct computation method to solve nonlinear Fredholm integral equation. So, we are going to discuss direct computation method for nonlinear Fredholm integral equation. So, equation is yx equal to fx plus lambda integral a to b k of x comma s g of ys ds, and this direct computation method to solve nonlinear Fredholm integral equation is applicable whenever this kernel is a separable kernel. So, that means we are assuming the kernel k x comma s is of the form sigma r runnings from 1 to n p r x q r s. This is the kernel. Now, for simplicity of understanding of the method by which we can solve this equation, we assume here k x comma s is only product of two functions p x and q s. Assuming this particular format, we are going to discuss about the direct computation method to solve this Fredholm integral equation, which is a nonlinear equation, and with illustrative example we will be considering that kernel is not a just product of two functions, one is a function of x and other is a function of x, but it is a sum of two this type of separable kernels. So, if we have this format for k x comma s, then the given nonlinear Fredholm integral equation can be written as yx equal to fx plus lambda px integral a to b qs g of ys ds. And you can recall that linear Fredholm integral equation with separable kernel we have considered and solved by using the direct computation method, where instead of g y s, here the terms appear to be a to b q r s y s d s, and we have assumed each of these integrals a to b q r s y s d s, those are constants. So, in the same manner here we assume beta equal to integral a to b q s g of y s d s, and therefore, we have y x is equal to f x plus beta lambda p x. So, this is a tentative expression for y x. Now, if we substitute this expression for y x equal to, that is f x plus beta lambda p x, into the definition for beta, we find that beta equal to integral a to b q s g of f s plus beta lambda p s d s. Depending upon the nature of this nonlinear function g and explicitly solvability of this integral, we can find an equation involving beta, and we can solve this equation for beta to get values or expression for beta in terms of the parameter lambda, and this lambda plays a crucial role in order to existence of solutions or existence of values or expression for beta, which you can see from the forthcoming examples. And depending upon the nature of the solution, if we substitute the expression for beta into the previous result, that is y x equal to f x plus beta lambda p x, we can find the solution to the given problem. So, this is actually the method of direct computation to solve nonlinear Volterra integral equation. So, first we consider one example. Y x is equal to 1 plus lambda integral 0 to 1 s y square s ds. This is the given problem. So, we assume beta equal to integral 0 to 1 s y square s ds. With this assumption, from the given equation we find y x, this is equal to 1 plus beta lambda. Now, if we substitute this expression for y x in the expression for beta, then we can find beta equal to integral 0 to 1 s 1 plus beta lambda whole square ds, and evaluating this integral we find this is equal to 1 plus beta lambda whole square multiplied by half, and rearranging the terms of beta from both sides we can find a quadratic equation for beta as beta square lambda square plus 2 beta multiplied with lambda minus 1 plus 1, this is equal to 0. So, this is a quadratic equation in beta whose coefficients are functions of lambda, and solving for beta we can find beta equal to 2 into 1 minus lambda plus minus root over 4 lambda minus 1 whole square minus 4 lambda square divided by 2 lambda square, and after simplification this comes out to be 1 minus lambda plus minus root over 1 minus 2 lambda divided by lambda square. So, these are actually two values of beta. Now, in this case if we assume that y x is a real valued function, then integral 0 to 1 s y square s ds should be a real constant, and therefore, for real values of beta from this expression we are getting a restriction on lambda, that is 1 minus 2 lambda should be greater than equal to 0. So, real values of beta can be obtained for lambda, this is less than equal to half, and substituting these expressions for beta into 1 plus beta lambda, we can find that two solutions are given by y x is equal to 1 plus minus root over 1 minus 2 lambda divided by lambda. Now, this expression is little bit interesting in the sense, first of all you can observe that whenever lambda less than half we find two solutions. One is 1 plus root over 1 minus 2 lambda divided by lambda, and other is 1 minus root over 1 minus 2 lambda divided by lambda. So, this clearly shows that the problem has two solutions. So, therefore, we are not getting unique solution for the given problem, although both these solutions are actually constant. So, that means y x equal to constant, this is a solution to the nonlinear integral equation, but we are getting two solutions. Secondly, both these solution coincides to the one solution whenever lambda equal to half. For lambda equal to half, we can find that both the solution coincides to 2 only. So, now this is the most important point, that lambda equal to half, this is actually called bifurcation point, and the phenomena that for lambda equal to half we have only one solution, for lambda less than half we are getting two solutions, that is 1 plus root over 1 minus 2 lambda by lambda and 1 minus root over 1 minus 2 lambda by lambda. These two solutions are actually bifurcating from the unique solutions obtained at lambda equal to half. So, this phenomena is called bifurcation of solutions, and this type of bifurcation actually appears in most of the discussions on nonlinear dynamics involved with nonlinear equations. So, this is one simple example of nonlinear integral equation where bifurcation of solutions may comes into the picture. And another important aspect is that if we consider that lambda equal to 0, if we consider lambda equal to 0, from the given problem we find y x equal to 1 is a solution, and this particular solution y x equal to 1 cannot be obtained from the solution that we have derived, that is y x equal to 1 plus minus root over 1 minus 2 lambda divided by lambda, and this particular solution y x equal to 1 is actually called the singular solution. And another important observation is that as y x equal to 1 plus minus root over 1 minus 2 lambda divided by lambda, so there does not exist any real solution whenever lambda greater than half. So, with help of this particular simple example, we have explained 3 important points. Number 1, the concept of bifurcation of solution. Number 2, the existence of singular solution, and number 3, that solution depends upon the parameter. For certain range of values of lambda we are getting 2 solutions, and for certain range of values of lambda there does not exist any real solution for the given problem. So, all these situations most of the time come up with the case of nonlinear integral equation. Now, we consider one more example of a nonlinear Fredholm integral equation where lambda is exactly equal to 1. So, that means there is no parameter is involved, equation is free from the parameter. With this example that just we have considered, it appears to our mind that whenever lambda is involved, then we can find 2 solutions. But next example will explain that instead of for a particular value of lambda, still for nonlinear integral equation we can have more than one solution. So, in that case also there is no question of uniqueness of the solutions. Second example is y x, this is equal to x minus 5 by 6 plus integral 0 to 1 y s plus y square s ds. So, this y s plus y square s in this case is actually our g s, although this y s separately is a linear function, but y s plus y square s is a nonlinear function. Now, we define 2 quantities beta 1 and beta 2, they are defined respectively by 0 to 1 y s ds and beta 2, this is equal to integral 0 to 1 y square s ds. So, with these definitions we can write the given equation is y x is equal to x minus 5 by 6 plus beta 1 plus beta 2. So, using these tentative expressions for y x, that is equal to x minus 5 by 6 plus beta 1 plus beta 2, in the formula for beta 1 we can find beta 1 that is equal to integral 0 to 1 s minus 5 by 6 plus beta 1 plus beta 2 ds, this is equal to half minus 5 by 6 plus beta 1 plus beta 2, this implies beta 1 equal to minus 1/3 plus beta 1 plus beta 2, and from here we find beta 2, this is equal to 1/3. So, just substituting y x into the expression for beta 1, immediately we have obtained beta 2 equal to 1/3, and hence y x is modified to x minus 5 by 6 plus beta 1 plus 1/3. So, that is equal to x minus half plus beta 1. This is the expression for yx, and substituting this expression into the expression for beta 2, we find 1/3 equal to beta 2 equal to integral 0 to 1 s minus half plus beta 1 whole square ds. So, this is equal to integral 0 to 1 s square ds plus 2 into beta 1 minus half integral 0 to 1 s ds plus beta 1 minus half whole square integral 0 to 1 ds. And after evaluating these integrals, we can find 1/3, that is equal to 1/3 plus beta 1 minus half plus beta 1 minus half this whole square. So, 1/3 cancels from both sides, and solving for beta 1, we find two values of beta 1 is actually plus minus half. So, already we have obtained that y equal to x minus half plus beta 1. So, therefore, substituting beta 1 equal to half, we find y equal to x is a solution, and for beta 1 is equal to minus half, we find y equal to x minus 1 is a solution. So, although the given problem does not possesses any particular parameter like lambda, but still the nonlinear integral equation possesses two solutions. One is yx equal to x and other one is yx is equal to x minus 1. So, this is actually the method of direct computation by which you can solve the Fredholm integral equations, which are nonlinear integral equations with separable kernels. Now, we just look at the Adamian decomposition method, how that particular method can be applicable to the case of solving nonlinear Fredholm integral equation. So, we are going to use the decomposition method. To solve nonlinear Fredholm integral equation is given by yx equal to fx plus lambda integral a to b k of x comma s g of ys ds. So, first of all, we can assume the form of yx as sigma n runnings from 0 to infinity y n x, and this Adamian decomposition method says we have to assume a form for g y x also, where g y x, this is assumed to be summation n runnings from 0 to infinity b n x. Now, you just try to understand in the previous examples, for example, where g y was equal to y square, then if we assume y x is equal to n runnings from 0 to infinity y n x, and we assume g y x equal to sigma n runnings from 0 to infinity b n x, for existence of the solution and validity of this technique, we need some relations should be satisfied by y n and beta n's. I am not going to prove the result from where we can get this relation, but for general nonlinear function g, we can define first few iterates which shows the relation between b0, b1, b2, b3 and so on with y0, y1, y2 and so on. So, these relations are given by b0 x, this is equal to g of y0 x, this one. then b1x this is equal to y1x multiplied with g dot y0x. Here g dot y0x means we have to differentiate gy with respect to y, and then substituting y equal to y0x we can find g dot y0x. Then b2 x this is equal to y2x g dot y0x plus y1 square x by 2 or factorial to g double dot y0x. Then b3 x this is equal to y3x g dot y0x plus y1x y2x g double dot y0x plus y1 cube x divided by factorial 3 g triple dot y0x and so on. So, in this way we can find the relations between b0, b1, b2, b3 and so on with y0, y1, y2, y3, and expressions for b0, b1, b2, b3 in terms of y0, y1, y2 and so on is determined by the nature of the nonlinear functions. So, there is no unique expressions for b0, b1, b2 in terms of explicitly y0, y1, y2, but those are determined by the nature of the function g. Once with these particular expressions, now if we substitute the expression for yx and gyx into the given integral equation, then we find sigma n runnings from 0 to infinity ynx this is equal to fx plus lambda integral 0 to infinity k of x comma s sigma n runnings from 0 to infinity b n s ds, and assuming the interchangeability of the integral and the summation, and then equating the terms from both sides following this rule that y0x equal to fx, then y1x is equal to lambda integral a to b k of x comma s b0s ds, b0s ds, then y2x is equal to lambda integral a to b k of x comma s b1s ds and so on. So, we can find out y0, y1, y2 and so on. Now, with this assumption, if you just recall the expressions for b0, b1 and so on, you can see that b0x is a function of y0 only. So, first of all we are assuming that y0x equal to fx, that means we are equating y0x from left side with fx on the right hand side. So, that means with this result y0x equal to fx, now y0 is known. Next we equate y1x from left side with the term lambda integral a to b k x comma s b0 s ds from the right. So, now b0 s is known because b0 is a function of y0 only, and therefore, we can evaluate this y1x. Once y1x is known, then using the relation between b0 b1 and y0 y1, we can understand that now b1x is a known function. So, once b1x is a known function, then equating y2x from the left with lambda integral a to b k x s b1 s ds, we can find y2x. So, proceeding in this way, we can find the terms, that is the Adamian polynomials y0, y1, y2, y3 and so on, and summing up with all these terms, we can find solution to the given problem. So, in the compact form we can write that y0 x is equal to f x and y n plus 1 x, this is equal to lambda integral a to b k of x comma s b n s ds. This is valid for n greater than equal to 0. So, using this formula we can calculate the iterates or the you can say Adamian polynomials y0, y1 and so on, and using the relation between b0, b1, b2 with y0, y1, y2 and so on. Now, we first consider the relation between b0, b1, b2 with y0, y1, y2 for the particular case, that is g y is equal to y square, and then we use these expressions in order to find out solution of an nonlinear Fredholm integral equation involving the term y square s. So, as per results that we have written, b0 x is equal to y0 square x, b1 x this is equal to y1 x into 2 y0 x, g y equal to y square, g dot y equal to 2 y, this 2 y evaluated at y0 x gives 2 y0 x. So, therefore, b1 x will be 2 y0 x into y1 x, then b2 x is equal to y2 x multiplied with 2 y0 x plus y1 square x by 2 into 2, because second derivative of g with respect to y is 2 and therefore, g double dot y0 is simply 2 and therefore, b2 x is comes out to be 2 y0 x multiplied with y2 x plus y1 square x, then b3 x this is equal to y3 x multiplied with 2 y0 x plus y1 x y2 x into g double dot y0 x. So, this is 2 and last term is equal to 0, because third derivative of g with respect to y is 0. So, therefore, b3 x is equal to 2 y0 x y3 x plus 2 y1 x y2 x, and you can find next iterates. Now, we use these results for b0, b1, b2, b3 in terms of y0, y1, y2, y3 for g y equal to y square in order to solve a nonlinear Fredholm integral equation. And here we are going to solve the same example that we first considered, which we have solved using direct computation method, and that is the equation y x is equal to 1 plus lambda integral 0 to 1 s of y square s ds. So, here f x equal to 1. So, using the formula y0 x equal to f x, we can find y0 x equal to 1. Then y1 x, that is equal to lambda times integral 0 to 1 s b0 s ds. Now, b0 s is equal to y0 s. So, this is 1. So, this will comes out to be lambda by 2. Then y2 x equal to lambda integral 0 to 1 s b1 s ds. Now, b1 x it was 2 y0 y1 x, y0 equal to 1 y1x equal to lambda by 2. So, this will be equal to lambda integral 0 to 1 s into 2 into 1 into lambda by 2 ds, and this will be equal to lambda square by 2. And similarly, y 3x is equal to lambda integral 0 to 1 s b 2 s ds, and this is equal to lambda integral 0 to 1 s 2 into 1 into lambda square by 2 plus lambda square by 4 ds, because b 2 x was 2 y 0 x y 2 x plus y 1 square x. So, that means 2 into 1 into lambda square by 2 plus lambda by 2 whole square. So, this one, and after evaluating the integral and little bit simplification, we find this is equal to 5 lambda cube divided by 8. So, therefore, adding these particular quantities 1 lambda by 2 lambda square by 2 and 5 lambda cube by 8, we find solution to the given problem is 1 plus lambda by 2 plus lambda square divided by 2 plus 5 lambda cube divided by 8 plus dot dot up to infinity. This is the solution. Now, in this case we have a nonlinear equation. This equation, when we have solved with respect using the direct computation method, then we have obtained two solutions, and here we are getting one solution, and now we have to verify whether this solution is matching with any one of them or not. So, that means this gives us a new solution apart from what we have obtained earlier or not, that we have to verify. But if you calculate this expression, that is 1 minus 2 lambda, the square root. So, that is actually 1 minus 2 lambda whole to the power half, and expanding this particular quantity in a negative binomial series and assuming that 2 lambda less than 1, therefore, you can find that lambda less than half restriction will come out from the condition for binomial series expansion of this particular expression, and after expanding in binomial series, you find this is equal to 1 minus lambda minus lambda square by 2 minus lambda cube divided by 2 minus 5 lambda to the power 4 divided by 8 minus dot dot up to infinity. And with this expression for root over 1 minus 2 lambda, you can find 1 minus root over 1 minus 2 lambda divided by lambda. This is equal to 1 plus lambda by 2 plus lambda square by 2 plus 5 lambda cube divided by 8 plus dot dot up to infinity. So, that means it is matching with the solution what we have obtained with Adamian decomposition method. So, by this you can verify that Adamian decomposition method is not giving you a new solution which is not coincident with either of the solution what we have obtained from direct computation method, but this method has a limitation for this particular problem, that it fails to capture or produce the other solution, that is 1 plus root over 1 minus 2 lambda divided by lambda. So, with this example, on one side we are try to understand how the method works in order to find out solution this problem, and also this method has a limitation that it is unable to capture or unable to produce both the solutions what we have obtained by direct computation method. And of course, you can apply this type of Adamian decomposition method for Volterra integral equations also. So, in that case, decomposition method for nonlinear Volterra integral equations we have only one difference, that is with the evaluation of the iterates. Here y 0 x will be equal to f x and y n plus 1 x, this will be equal to lambda integral a to x k of x comma s b n s d s. So, these are the formula for evaluating the iterates y 0, y 1 and so on for Volterra integral equation, that is nonlinear Volterra integral equation, which is given by, that is y x is equal to f x plus lambda integral a to x k of x comma s g of y s d s, and of course, in this formula b n s, these are defined as earlier. I am not going to consider any particular example here. You can find some examples in several places and try to solve it at your own. Next, we come to the series solution method. For nonlinear Volterra integral equations. Although I have written here nonlinear Volterra integral equation, but method that we are going to discuss, that is for a specific type of nonlinear Volterra integral equations, those are given by y x is equal to f x plus lambda integral a to x k of x comma s y n s d s. Once we will be discussing the method, then you can understand why I am considering here the particular form y to the power n here, and that is just for simplicity and understanding of the method. The method is that we assume that this equation possesses a series solution of the form sigma m running from 0 to infinity C m x to the power m. So, that means we are intended to find a solution in this particular format C 0 plus C 1 x plus C 2 x square plus C 3 x cube plus dot dot up to infinity. Now, in case of y to the power n, we can calculate first few terms of y n x, and for example, say these are denoted by d 0 plus d 1 x plus d 2 x square plus d 3 x cube and so on. Then substituting these two expressions into the given equation, and after evaluating the integrals, we can equate like powers of x from both sides. And here this d 0, d 1, d 2, d 3 and so on, all of them are actually functions of C 0, C 1, C 2 and so on. So, depending upon the evaluation of this d 0, d 1, d 2 in terms of C 0, C 1, C 2, and then equating the like powers of x from the both sides, we have some nonlinear system of equations for these unknown quantities C 0, C 1, C 2 and so on. So, if we are able to solve those nonlinear algebraic equations involving C 0, C 1, C 2 and so on, we will be able to find out solution of this particular problem, and we can explain this idea with help of one example. We consider this example, that is y x is equal to 1 minus x square minus x cube by 3 plus integral 0 to x y square s ds. Here we are assuming y x is equal to sigma n running from 0 to infinity C n x to the power n. So, now if we calculate y square x, so that is equal to sigma n running from 0 to infinity C n x n whole square, and looking at first few terms of this particular series, we can find this is equal to C 0 square plus 2 C 0 C 1 x plus C 1 square plus 2 C 0 C 2 x square plus dot dot up to infinity. So, if you just compare with the previous discussion, that d 0 is now equal to C 0 square, d 1 is equal to 2 C 0 C 1, d 2 equal to C 1 square plus 2 C 0 C 2 and so on. So, this relation between d 0, d 1, d 2, d 3 and so on can be obtained in terms of C 0, C 1, C 2 in the cases where nonlinear functions involved with the nonlinear integral equation is of the form y to the power n x. In other cases, it is very difficult to find out this type of relation between d j's with c i's. Now, if we substitute this expression into the given integral equation, then we actually find that sigma n running from 0 to infinity C n x to the power n, that is equal to 1 minus x square minus x cube by 3 plus integral 0 to x C 0 square plus 2 C 0 C 1 s plus C 1 square plus 2 C 0 C 2 s square plus dot dot up to infinity ds. And therefore, after evaluating this integral, we find C 0 plus C 1 x plus C 2 x square plus C 3 x cube plus dot dot up to infinity. This is equal to 1 minus x square minus x cube by 3 plus C 0 square x plus C 0 C 1 x square plus C 1 square to C 0 C 2 x cube divided by 3 plus dot dot up to infinity. After rearranging these terms, we find this is equal to 1 plus C 0 square x plus C 0 C 1 minus 1 into x square plus C 1 square plus 2 C 0 C 2 minus 1 x cube plus dot dot up to infinity. Then equating like powers from both sides, we find C 0 equal to 1, then C 1 is equal to C 0 square, C 2 this is equal to C 0 C 1 minus 1, then C 3 this is equal to 1/3 C 1 square plus 2 C 0 C 2 minus 1 and so on. So, from the first relation we find C 0 this is equal to 1, from the second, that is C 1 equal to C 0 square, we find C 1 equal to 1, then C 2 is equal to 0, because C 2 equal to C 0 C 1 minus 1. So, 1 minus 1 equal to 0, then C 3 this is equal to C 1 square plus 2 C 0 C 2 minus 1/3. So, substituting there you can find this is also equal to 0, and you can verify all other constants, that is C 4 and onwards. If you solve this, you find all of them are exactly equal to 0, and therefore, the series for y x comes out to be, that is 1 plus x, and you can verify this y x equal to 1 plus x is solution to the nonlinear equation. So, in case this nonlinear function involved with the Volterra integral equation is of the form y n x, then you can make an attempt to solve this type of nonlinear Volterra integral equation with help of this series solution method. So, at this point I stop discussions on this nonlinear integral equation, but before completing this lecture I like to mention that the materials I have covered in this lecture, these are available in 4 books. These 4 books are: number 1, a first course in integral equations by A. M. was, this is a world scientific book. Then number 2, Introduction to Integral Equations with Applications, A. J. Zeri. Number 3, Linear Integral Equations by R. P. Kanwal, and number 4, the chapter on integral equation under this book, that is methods of applied mathematics by F. B. Hildebrand. And if you are interested to have a look to some advanced level books, then these 2 books are very well written books. Number 1, that is Integral Equations by F. G. Tricomi, and the book that is Linear Integral Equations by W. V. Lovett. And before concluding, I just like to remark that in all these books you find several discussions on integral equations, is method of solution and other advanced level treatment, but in the book by was the Adamian decomposition method and modified Adamian decomposition method are discussed, and in that book you find some further references where some advanced techniques for Adamian decomposition method to solve some complicated linear and nonlinear integral equations are also discussed. So, in this lecture series we are mainly focused on linear integral equations, but in the last lecture I just considered 2-3 examples on nonlinear integral equation. Just want to give you the essence of bifurcation, concept of bifurcation involved with the nonlinear integral equations. So, thank you for your attention.